This and the next video are two of the most important videos in this course. These have immense practical applications, and if you understand these two videos very well, the concepts are very simple, they're very straightforward, they're logical, they don't even have a lot of maths in them. It's all code. But if you understand these, you can take your machine learning and data science skills to the next level. A lot of people have trouble understanding advanced models in data science and machine learning because they don't have these core skills. So make sure that you pay attention over here, and if you have any ambiguities at all, please do post questions. The concepts themselves are fairly simple. You'll see that once you understand them, they're very logical, they're very visual, they're very easy to understand, no deep maths, no really complicated stuff going on, but people don't really spend time on this. So we are going to spend some time on this so that you understand them well. Here's what we're doing. We have seen the joint probabilities for discrete random variables. We saw that in the bag I has I blue balls and 2 green balls problem. Now we are going to take a look at joint distributions for continuous random variables. And it's the same concept, but visually it's slightly different. So let's go ahead and do this through code first and then on the paper. Okay. So we are going to import NumPy and we are going to set the seed to 1337 as before. We are going to import matplotlib. We are going to generate some random variables, right? So a very large number, we are going to generate these samples and we are going to give it this 2 over here. This 2 means that we want a 2-dimensional array, right? What this says is, this guy over here, this says generate values from 0 to 1 in a 2-dimensional array, and this is going to be the number of values that we have. Okay, once we have these values, multiply them by 10, so all the values go up by a factor of 10, and then you add 100. So whatever was 0 before now turns into 100, whatever was 2 before now turns into 120. Okay, so we are essentially moving these away from 0. Then we are going to create a histogram, not visually, but we are going to take the value, give it the bins, and np.histogram.dd essentially takes the values and converts them into a histogram, but not visually. It's going to give us the values back from which we can generate the histogram. So let's first output the values and then you see what this means. Okay, so it gives you back the histogram. So if you recall, a histogram looks like that. It has some bars which have the height, which is the value, and it has some places where the bars meet. So those are called edges. So this function is going to give you the values for the bar heights and it's going to give you the edges. So if you have the data divided into 5 bins, you are going to have 6 edges. So we don't want the very first one, so we get rid of that and then we output it. So this is what the edges look like. So let's go back. This is a lot of dense code. This is generating some values for you, this number of samples, but in a 2-dimensional array. Okay, then we are simply moving them around and rescaling them so that they make a lot more sense in our visual representation. Okay, then we are creating the histogram for each of the num samples that we've created. It's going to take that number. For instance, if it falls into 2,6, it's going to put it into the bin which is 2,6. So that gets incremented by 1. So these values are going to be the frequencies. So we are going to have a joint probability table. We can output the shape of this. So this is 5,5 because we have 5 bins. So the first axis is going to have 5 bins and the other axis is going to have 5 bins. So our joint probs table is a 5 by 5 array. Okay, hope that makes sense. If you want to look at the shape of the actual data, so data.shape was 1,000,000,2, which is essentially 1,000,000 pairs of values, right? So XY, 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 1,000,000 of those. Okay, so that is what our data is, and our joint probability distribution is calculated from that. So you take a pair, you see which bin it goes into, you put it there, and you increment the frequency based on that, and that is what you get over here. So a lot of zeros and a lot of very large values. So it's very difficult to look at them like this. So we are going to represent them visually, and this is what we're going to do. I'm sure you understand that if you just look at the code over here, it's very difficult. And that is the whole point of this video, that you need to visualize this either mentally or through code. Once you visualize it through code enough times and your brain has been sufficiently exercised, then when you look at this stuff, your brain is automatically going to create a mental image for it. And that is where the real strength of data science and machine learning comes in. Once your brain is able to take the numbers and visualize them internally, that is the whole point of this video. Okay, so I understand if this looks really complicated and really messy at the moment. Okay, that's the whole point of it. So what we're going to do is we are going to take this table and we are going to cut, for instance, on this row. Okay, so we are going to say, just show me the values of this one row. So that is going to be our cut point. We are going to take the x vals. So these are going to be from joint probs. We are going to take the second value. So this is joint probs. We take this. So those are our x vals. We divide all of those values by their sum so that they are normalized to lie between 0 and 1. I have a brain twister over here. Why do we need this cast? This joint probs cut point is already an NP array. Why do we need an extra cast over here? Think about it. If you can't figure it out, post questions and we'll discuss this. Okay, but this is necessary. If you don't do this, this is really problematic. Okay. Now, y vals. How do you get the y vals? You are going to go to joint probs again. You are going to take all the rows, but for columns you are going to take the cut point, which is 2. So this essentially is going to take 0, 1, 2, 2, 2, 2, 2, all of these values. So this is the column index 2. So we've got these y values over here, right? So we got these x values and we got these y values. We're going to plot them separately. Okay. We are going to print the edges. So these are the edges, right? So these are the values for edges. These are the x vals and these are the y vals. Okay. We are going to plot the x vals first. So this is what it looks like. So it is a bell curve, but because we have just 5 bins and these 2 bins are extremely empty, therefore this looks really bad. We're going to increase the number of bins and see how this affects our visual representation. Y vals also look like a bell curve. Why are they both individually looking like bell curves? Because they have been generated from over here using rand_n, which generates random variables from random distributions, and this too simply means give me 2 different values, and we know from the documentation of NumPy that these are going to be independent. They are not going to be affected by each other. Okay, now let's go ahead and try to look at them at the same time. If you go over here, this is what they look like at the same time. If you try to plot them, this is going to definitely turn into a 3D plot, and we don't really know how to work with that. So for x val is equal to 0 and y val is equal to 0, this is what we get. For x val is equal to 1 and y val is equal to 0, this is the value, and so on. So imagine that you have a grid on your table, on the desktop, not your computer desktop, the desk that you're sitting on. You have a grid over there. On the horizontal axis is the x plot and on the vertical axis is the y plot. And this value, where does this value then go? It has to rise up above from the table, right? So this is going to be a 3D plot. We're going to show this. I am intentionally trying to explain this without showing it to you so that your brain gets exercised. We are going to show this in just a minute. So what we want is, we want an x axis and a y axis, which are over here. And then we want a z axis, right? So a z axis is going to actually hold the values that we have for the joint probabilities, okay? So you have a table, you put that on the desk flat, and the values that you see in the cells are going to be heights, which are going to come up above from the table, okay? So how do you create this 3D plot? It's called a mesh grid. And for that, what you do is you take the x, which are edges 0, the y edges, which are edges 1. So go back over here and take a look at your edges. You have to keep going back and forth. So this is your x edges and these are your y edges. Okay, so you take them, you essentially create their Cartesian product, which is done using mesh grid. So this essentially creates a mesh grid for you. So for x comma y values, you are going to have some particular values, and those values are going to come from joint probabilities divided by their sum. So we are essentially normalizing this again. Okay, so this is just normalization. Let's visualize this, and then this is also going to make a lot more sense. Okay, so we are going to plot this, and this is plotted using a function called plot_surface, which is going to create a 3D plot. You give it an x, you give it a y, and then you give it a z, which is the height. So these are the 3 coordinates, and then you have some visualization parameters over here. Okay, and you are going to initialize the view at 45 degrees and 30 degrees of angle, right? So let's show that, and then it's going to make sense. So this is your x, this is flat on the surface, this is your y, and where are these values coming from? These are coming from the z axis, which is joint probs based on that. So here's how to look at it visually. For a value of x is equal to 100, this guy over here, and y is equal to 100. So you create a cross over here. This value is pretty high. Okay. At x is equal to 140 and y is equal to 140, this is where you come. So this portion is quite low in height. If you keep y fixed and you increase x, the probability goes up. If you keep increasing further, it goes down. If you fix x at, let's say, 90 or so, or 100, and you decrease y, your probability goes up. If you keep decreasing, it goes down. So the height is what is showing us the probability for those pairs of values. So the highest probability that we have in this data is the combination where y is 100 and x is 100. Okay, and the combination of 80, 80 is fairly low. The combination 140, 140 is very rarely occurring. That is what it's saying. Okay. So this, I hope this makes sort of sense. You can go ahead and change these different values to experiment with them. But the point is that this plot actually shows you which are the most frequently occurring values for these two variables. So you've taken the joint probability table and converted it into this 3D plot. The problem with this 3D plot is it's very difficult to work with this because we cannot see half of it. The other half we cannot see. We can rotate it using these values. We can even have an interactive plot which we can rotate, but at any point in time, we can only see like 75% of this plot. We cannot see the rest. So what we want to do is we want to take this plot and convert it into a 2D plot, because 2D plots, we can see all of them at the same time. But how do you take three different coordinates and convert them into a 2D plot? This is an extremely important concept. It's extremely simple. So I'm going to explain it here, but this is really what differentiates people who understand data science from those who don't. So please make sure that you understand this. Okay. So it's extremely simple. Here's what you do. You take all the values. The actual probability is represented using the height of this mountain. Okay. So this guy over here is a very high probability. So we are going to color code whatever the highest value is as a yellow, and the lowest values are going to be encoded using a dark color. Okay, so dark color and light color. We do that. Once that is done, we simply go ahead and squish this mountain from the top, right? So I don't know, how do you squish a mountain? You throw another really big mountain on top of it, so it gets squished, and it's going to look like this. Okay, so if you look at it from the top, this exact plot looks now like this. You first color coded it and then you squished it, which got rid of all the height, but the height information has been saved in the colors. So if we look at this plot, we can see that the values at 140, 140 are very dark. So they were very low probability. The values at 110, 110 are fairly large. Okay. Why? Because they have a lighter color. Lighter color means more height means more probability. So this plot is called a contour plot, and it's extremely, extremely important. We are going to take this to the notebook and try to understand what's going on over here in terms of the behavior of X and Y, and how this plot gives us a lot more information than we've seen up until now.